Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This section is dedicated to a wrap-up of everything you've learned in the curve sketching department, I guess you could say, of differential calculus. So you've worked with local maximums, local minimums, absolute maximums, absolute minimums. You had Fermat's theorem, which is not really Fermat's theorem, but it's Fermat's internal extremum theorem. And you've also dealt with things like L'Hopital's rule. L'Hopital's rule is really going to help us with end behavior. And then somewhere in there, you also started sketching curves using the derivatives, right? The first derivative test, the second derivative test, concavity, points of inflection, all that stuff. Before we go any further, we just need one last little piece of information, and that's the calculus of slant asymptotes. And I actually like to call these oblique asymptotes, honestly, because, excuse me, slant asymptote only works if you have an asymptote that's maybe a line, like a 3x plus 10 or something like that. But in reality, an oblique asymptote is anything that is, it exhibits the end behavior of the function. It doesn't need to be a line. So it could be a parabolic path or something like that. So this definition, which is actually straight from a textbook, is really not precise enough, in my opinion. But I'm going to stick with it because this is really what most students learn. So what is a slant asymptote? Everybody knows it's the slant asymptote from your pre-calculus course is kind of the end behavior of a curve. You know, like you have some asymptote like that. You might have your curve do something, whoops, well, that actually works, that's fine. Something like this, you might have a vertical asymptote there, and maybe over here your curve does something like that. And so we would say that behavior, which might be y is equal to 3x plus 5 or some silliness like that, that is the slant asymptote, because the long-term behavior of your curve tends to, as you zoom out, look like the slant asymptote. However, like I said, it doesn't need to just always be a line. It could be a parabola or something like that. Also, that definition from pre-calculus really is not rigorous enough. It doesn't really cover all the bases. So if we have some function, and I'm calling it s of x for slant, if we have some function mx plus b, and we have the fact that the limit as x goes to infinity or negative infinity, I should have both plus or minus infinity, but we'll just deal with one side. As x goes to infinity, that difference between your function and that slant asymptote, if that tends to 0, then that function s is actually defined to be the slant asymptote of the function. And that's exactly what the definition is. Now, like I said, there's a slight modification here because you also want, let's say there's a different function t such that the limit as x approaches negative infinity of f of x minus t of x. If that ends up being 0, then t is called a slant asymptote as well, and just in the negative direction, but it's also called a slant asymptote. There are cases, very rare as they may seem, there are cases when your function might have two completely different asymptotes at the ends of your function, or at the ends of the graph. So to the right, it might behave like a cubic, and to the left, it might tend to a horizontal line or something like that. So that's just a heads up. All right, so now that we have that defined, how do you use this definition? It's actually pretty simple, and I'm going to give you a basic guideline that works pretty much flawlessly. So in this case right here, this is a typical one that you would see in a pre-calculus or a college algebra or even an algebra course. Find the slant asymptote of the function. Back in algebra, you learned to do the following, which is actually going to be done in this course as well. You did a long division, right? Oh, x minus 2 goes into x squared plus 0x plus 12, And then you did this long division process. X goes into x squared, x times x gives me x squared. X times a negative 2 gives me a negative 2x. And then you're going to subtract that entire statement, right? So this should look familiar to you. X squared minus x squared is gone. 0x minus a negative 2x is a positive 2x, bring down the 12, and then just ask how many times does x go into 2x? Well, it goes in twice. And then you can multiply through. There's really no reason to, but we can multiply through and you'd get 2x minus 4. That's found from multiplying 2 times x and 2 times a negative 2. And again, you do that subtraction of that entire statement. The 2x's will cancel by design. 12 minus a negative 4, that'll give us a positive 16. Since x does not go into 16, 16 is called the remainder. Again, you guys know that from your pre-calculus course, but once you do that, you find that this can be written as the quotient, which is x plus 2, plus the remainder, which is 16, divided by the divisor, or over the divisor, whatever you want to call it. And as x goes to infinity, we know that this is going to disappear because that'd be 16 over an infinite number. And because it disappears, all that would remain is this linear part, those linear terms, I should say. So that's kind of how you did it in pre-calculus or maybe college algebra. In calculus, you're going to make the claim that x plus 2 is your slant asymptote. So the claim here is that the slant asymptote is y equals x plus 2. The proof of that claim comes from the definition of a slant asymptote. The definition of the slant asymptote, again, is that as x goes to positive or negative infinity, that the function gets infinitely close to that slant asymptote. In fact, the difference between them becomes 0. And again, you don't really have to prove it in both directions, but you could if you wanted to. You could put plus as x approaches plus or minus infinity. The same issue would, or the same situation would occur for most functions, specifically rational functions. So proving this claim, we'll just say the limit as x goes to, I like to say plus or minus infinity here, mainly when I'm dealing with rational functions. We'll see examples where we have functions that only have slant asymptotes in one direction. We'll see that in a while, maybe actually pretty quickly. But we'll take our function, which is x squared plus 12 divided by x minus 2. That's our function, f of x there. And we're going to find the difference between that and our supposed slant asymptote, x plus 2. That's our supposed slant asymptote. So we're just taking the difference between those. Well, we already know through long division that x squared plus 12 over x minus 2 becomes the following. So limit as x goes to plus or minus infinity of x plus 2 plus 16 over x minus 2. And we are subtracting the supposed slant asymptote. Well, you can see in this case, the x's will cancel beautifully, and so will the 2's. And you end up with a very easy limit. The limit as x approaches plus or minus infinity of 16 over x minus 2. And we can easily recall, hopefully that you can, that 16 over something approaching infinity is essentially 0. So that limit is 0. And that is what you want, actually. The limit, you want that limit of that difference to become 0. If it is true that that happens, then you have proven the claim that the slant asymptote you're dealing with is x plus 2. Well, QED. We have proven that statement. It is pretty much that easy for rational functions. If you don't have a rational function, well, all bets are off. For example, if you have this function right here, f of x is equal to 1 minus x plus e raised to the 1 plus x over 3. This is a very fun function, and it does actually have a slant asymptote. You just wouldn't expect that it would, but it does. To find the slant asymptote, just imagine, without even writing anything down, imagine what would happen as x goes to infinity. If something, actually, maybe I should write this down because this is actually a really important point to make. So if you're given a function and if a term or several terms disappear as x goes to infinity or x goes to negative infinity, it doesn't have to be both, it could just be one. The remaining expression that doesn't disappear is really the end behavior of your function. And if that remaining expression is a linear function, then we would call it a slant asymptote or an oblique asymptote. If it's not linear, it still is the end behavior of your function. It's just kind of neat. Although, to be honest with you, if it's non-linear, the end behavior can get a little bit wacky. So we generally don't worry too much about non-linear end behavior. However, I'll give a few examples just so that you could see that as we move forward. So in this case, here's a function. Does any term of this disappear, mean completely just tend to 0 as x goes to positive infinity? Well, 1 does not, because it's 1 forever. Negative x doesn't, because, well, as x goes to infinity, negative x goes to negative infinity. It definitely does not disappear. And e to the power doesn't as well, because that would be e to the infinite power, which tends to infinity. So as x goes to infinity, nothing disappears. In fact, let me write that down. Now let's investigate as x goes to negative infinity, because we do have to investigate both directions. As I mentioned previously, you can actually have a function that has a slant asymptote only in one direction. So as x goes to negative infinity, well, again, 1 is always 1. And negative x would actually go to negative infinity or positive infinity. So again, that doesn't disappear. However, e to the power, well, as x goes to negative infinity, e to the negative infinite power will tend to 0. That expression or term will disappear. And what we would have left is a 1 minus x. So we actually do have a supposed slant asymptote to this function as x goes to negative infinity. And this means that we have that, well, I already just said it. We have a slant asymptote at 1 minus x. So I'm just going to write that down. This implies 1 minus x, actually I should say y equals 1 minus x. And maybe I'll even say s of x is equal to 1 minus x is a slant. We still have to prove it, but it's a slant or oblique asymptote. I'll just put a dot as x goes to negative infinity. Okay, it's still something that we have to prove. We can't just say, oh, our slant asymptote is 1 minus x. I will, if you're one of my students, I will say, prove it. And the proof is incredibly fast. So it's not like it's taking a lot of your time to prove that something is a slant asymptote of a function. You just make the claim. My claim is that y equals 1 minus x is a slant asymptote. I'll just do it that way, slant asymptote. By the way, I'll sometimes write oblique asymptote. I kind of like the word oblique better than slant. So I'll write oblique asymptote as x tends to negative infinity. The proof, very, very quick, goes like this. By definition, remember the definition of an oblique or a slant asymptote is that the limit of the distance between your given function and your supposed slant asymptote tends to 0 as x goes to, in this case, negative infinity. So the limit as x goes to negative infinity of our function, I'm not going to bother writing that. I'll just write 1 minus x plus e to the 1 plus x over 3 minus our supposed oblique. Well, you could see that in this case, the 1s will cancel beautifully and so will the negative x's. And you're left with the limit, again, as x goes to negative infinity of e to the 1 plus x over 3. Now, it depends on who your instructor is and how rigorous they want you to be with this. But to me, I would just say, well, that power is going to negative infinity and e to the negative infinite power is 0. But if you have a very, very stringent instructor, they would require you to take your steps here. So I'll just go ahead and showcase the mathematics. This is e to the first times e to the x over third, which is e times the limit as x goes to negative infinity of e to the x over 3. And if they're still not satisfied, we have a limit law that says the limit of a function to a power is the power of the function of the limit of the function. That is, this is a cube root of e to the x. So the limit of the cubed root of e to the x is the same thing as the cubed root of the limit of that e to the x. This is just to foil anybody who has an issue with how I do things. And this is a theorem that tends to 0. So we have e times the cubed root of 0, which is 0. And so therefore we have proven that 1 minus x is the oblique asymptote for that function. When I say oblique, I mean slant. They mean the same thing. And I think oblique is a little more broad. It's a broader statement. Now let me rewind the tape here a couple steps, because I want to mention something that I used to teach. I don't want to really officially write it down here, but I'm going to say it out loud. While officially the definition for the oblique or slant asymptote is that the oblique or slant asymptote is a linear function, you can gain a lot of information by finding out what disappears from your function, from your given function, as x goes to positive or negative infinity, even if it's not a linear function. So if somebody hands me a function, f of x, is equal to, it really doesn't matter, let's say x times the square root of x to the third plus 1 minus 1 over x squared plus 2 plus e to the negative x. Well, as x goes to infinity, two of those terms, specifically this guy and this guy, disappear. And so the behavior of this function is modeled by the remaining function. That would not technically be called an oblique asymptote, but it sure does give me a good visual of the behavior. And you might look at that and say, how does that even give you the behavior? Or how do I even know how to graph that? Well, in the big picture, this is like the square root of x cubed in the big picture. Well, that just means x to the 3 halves. And you're multiplying it by x to the 2 halves, which is x to the 5 halves, which is basically like x to the power, right? It does something like this, or maybe something like this. It might be concave down, who knows? But it gives you an idea of the picture as time goes on. This is probably a bad example, but the idea is that you eventually, maybe it would have worked better if I had a 4th power. Let's do a 4th power. If you do a 4th power there, it's a lot easier, because then that behaves like an x squared times an x to the first, or like an x cubed. There you go. So as you look at this end behavior in the long run, it looks sort of like that. The rest of this stuff right here just disappears, actually only in the positive direction, because in the negative direction, e to the negative infinity is e to the positive infinity. That'll blow up. But at least in the positive direction, those two terms disappear, and it'll mimic e to the x, or x to the 3rd power. It's not an official definition. It's just something that might help you with your graphing. So again, you don't have to do it unless your instructor forces you. The key here is to note, as x gets massive, what disappears? Or as x gets negatively massive, what disappears? That's the whole point. All right, so that'll do it for slant asymptotes. So from this point forward, our laundry list of graphing, like the how-to on graphing using calculus, is now almost complete. There's one tiny little addition on top of the slant asymptote that we have to include. We'll see that in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.